So before I do this, let me tell you a bit more about the difference between a property and a structure. And to explain this, I will present the notion of a group, the definition of a group in two different ways. So let's start the usual ways that you see in school. So a group, according to many teachers, is a set G equipped with a binary operation, which we will denote by dot, satisfying the following properties. It is associative, okay? This is something we don't care about. It is not the problem. But they tell us there exists an element such that E satisfies this condition. So it is the identity element. Moreover, they tell us that for every element, there exists an inverse, which means that it satisfies this property. This is the standard definition. Now, this is definition asserts some properties for this element. So it tells you that there exists an element E satisfying a property. For every element A, there exists an element B satisfying a property. So this is what I mean by a property. You say there exists something which satisfies this and that. Okay? First of all, what is the problem of this definition? The problem is when you write this here, what do you mean by E? You would say, I mean the identity element, which we know exists from the second point. But this second point tells you there exists an E, but it can exist severally. So when you write this, what do you mean? Which E is it? You will say, okay, but we know that the identity is unique. Yes, that's correct. But to make this logically correct, you have to first make a lemma here that the identity is unique, and therefore you can make the third axiom. Logically speaking, that's what you should do. So you see, this approach, this definition is a bit misleading. And its problem is, as we will see, that the existence of this existential quantifiers in the axiom. This will be a huge problem. Of course, in the case of groups, we can avoid this, as is written here, because we can now give you a better definition of a group. And according to this definition, a group is a set given equipped with some binary operation and a unary operation I. So this also I denoted before dot minus one, which gives you the inverse, and a zero I operation, which means something like this, or just if you take the image, it is a distinguished element. And we now require the following to hold. For every A, B, and C, the following list of axioms hold. Do you see any existential quantifier? Do you see any properties? No. It is all about the structure. The point here is I encoded these existential quantifiers into part of the structure as maps. So I turned an existential quantifier into structure. And if I do this, what is the benefit? The benefit is that my axioms will be of the form for every two dots, some equation, something equals something, some equation, 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 equation. You see, no existential quantifier. This is insanely deep, and I will tell you why in 5 minutes. So this, I just want to keep you this distinction in your mind. You should keep it. So let's see the difference of this. So in groups, we have said that the product of two groups is a group, whereas the product of two fields is not a field. Why this is the case? Precisely of this phenomena, as we will see. Actually, I will prove it to you. In groups, we can somehow eliminate the existential quantifier, make it part of the structure by introducing these two maps. And this is just another way to assert the uniqueness of the identity and the uniqueness of the inverse, whenever they exist. For fields, we cannot do this. So one of the axioms of a field is every non-zero element has an inverse, which if you write formally, it tells you this thing here. And here you have an existential quantifier. And this existential quantifier can never be eliminated. You cannot make it into a part of the structure, because to do so, you will need to have a map like this. But this is not an operation. You remember the operation was from A to A, or from A cross A to A, but this is not of this form. So this is not an operation. And there is no way to make it into an operation. We will prove this. It's not a proof. I'm just telling you the outcome. And this ability to eliminate this existential quantifier is a very deep reason why the product of two fields is not a field. So the comparison is, in groups, we can eliminate the existential quantifier, and therefore we can write our axioms like for all, and then we have two equations. For fields, we cannot do this. So we cannot eliminate the existential quantifier. Okay, so let me tell you more about these equations and the existential quantifiers and all of this story. So a bit informal here as well. So we start with S as a fixed signature, and we have a collection of S algebras. Let's call it C. So C is just a collection of, let's say, groups, a collection of rings or whatever. Some fixed signature, you take some collection of algebras with this signature. And we will call this equational if there exists a collection of equations such that, I will tell you in a moment what's an equation, but hold with me, there exists a collection of equations M such that an algebra, a general algebra, is in C if and only if it satisfies this equation. This is the notation. This is just a different way to say that this equation holds true in this algebra. I will explain this more formally in a moment. I'm just giving you the flavor. So first of all, let's focus what is the equation. The equation is an operation, is a formula, is something like this. So we have some universal quantifiers, and then we have equality of two expressions, E1 and E2. And these expressions are just expressions consisting only of variables and operation symbols. So as an example, this thing here, you see x dot y equals y dot x. Here, my variable symbols are x and y. My operation symbol is the product, the dot. Here, in the case of heaps, we have variables x, y, and the operation symbol is t. So such a thing will be called what I mean here by this expression. And if we equate two of them, like in this case here or here, we get what we call an equation. So in particular, there is no existential quantifier, there is no implication, there is no not equal sign. Okay, and as we will see, fields are not equational, meaning you cannot find equations such that this happens, such that a ring is a field if and only if it satisfies this list of equations. So this is, we will more or less prove. So the examples we have seen so far, Boolean algebras, rings, heaps, Lie algebras are all equationals. And I have given here you a list of the equations. And you can check these are equations. You don't see any existential quantifier, you don't see any implication, and so on. So to define more precisely what is an equation, I to tell you about the notion of a term. So again, we will always fix a signature, and we will start with a set. And you should think of this set as a set of symbols. Sorry, a set of symbols for variables. So this is variables. And we will define an x term. So again, it is the same x. So I mean a term constructed from x to be the following. It is either an element of x, so it is either a variable, or it is a distinguished element of the algebra or of the signature. So for the case of the groups, it can be E. For rings, it can be 0 or 1. So this will be also called terms. So I start with variables and constants. So these constants are my distinguished elements. And these are my, so this definition, first of all, is done by induction. And these are somehow the base case, the starting point. And now I start building more and more complicated terms. And the way I do this, I start with some terms that I constructed in the beginning, for example, variables or constants, and I take an operation symbol, and I just put this operation symbol in front of this list of terms. So this is now, it is not an application of a function. It's just a symbol. This is just a symbol. And that's why it is very important in universal algebra to distinguish a symbol from a function. Here, this is just a symbol. So you can think of this as a sequence of symbols. Right? This is what is a term. So again, we start with variables, we start with constants, and we start inductively combining those with the operation symbols in a way to construct a more complicated and compound terms. And I will denote the set of all terms by Tx. So X is the set of variables. Because, I mean, the constants are fixed because we fix a signature from the beginning, from the outset. So the constants are fixed. So the only thing we are free to choose are the variables. So our notation only remembers the variable, right? So let me maybe give you an example. Yes. So let me give you an example. So let's take the case of theory of rings. And let's take our set of variables to have two variables, small x and small y. So we know that the constants of our case are 0 and 1. So we can start adding them. This means applying the symbols. And here I write this. Why do I write 1 plus 1 and not 2? Because I emphasize that this is just a symbol. This is not 2. I here write 2 to remind you intuitively it is 2. But formally, it is just a symbol. So we have something like this. And if we are going to use 2 or 3, it's just as notation, but it doesn't mean the number 2. It's just a symbol, right? Think of something you write on the paper. We can also construct the variables. So these are terms, and we can multiply here, and we can do this multiplication several times. And in this case, as a shorthand notation, it is not an equality or anything. I will write this x to power n, y to power m. And in this case, you see that all terms are just the polynomial ring or rings. If you do groups, you get something else. You get a list of what they call usually words. So you get a list of symbols. But for rings, it is something we know already. Okay, so this is the example you should keep in mind. But the whole point is that this set of terms is actually an S algebra. It's an algebra of the same type. So I need to tell you how to interpret the symbols, operation symbols, as actual operations. So here, if I have G is an in-array operation, I know this is dry a bit, but it is the only part of the top which is dry, I promise, but it will be also fulfilling in 2 minutes. We interpret this symbol to be the following function. So I take in many elements, which means in many terms, and I apply GTX to be just this term. So here, these are inputs. These are individual inputs. And here, this is the interpretation of the function inside Tx. And the output is just a new term, which I denote this. So this function GTx, it takes terms and gives me, spits out terms. And the term it takes is T1 up to Tn. The term it spits out is GT1 up to Tn. So this is why it is important to keep the distinction between a symbol and a function. This G here is just a symbol. This G here is a function. So if you don't keep these distinctions in universal algebra, very, very quickly you will be confused what is happening. Of course, to make, like, usually people are so pedantic about the precision to avoid this. So here today I am a bit informal with you. But if you go for a textbook, you will see a lot of formalism to make this distinction very, very clear. But if I do this, it will be very boring. It takes a lot of time to digest this formalism. But here I'm just trying to, make it a little bit informal. But in theory, you should be more precise. Okay. Now, I would like to tell you about a very important notion which will allow us to define this equation notion. And this notion I will tell you about is in itself very important. If you only go from this talk knowing about this notion, I will be satisfied. I will call it a day. So before I tell you the notion, I will just give you a special case of it to motivate it. So let's suppose that we have a ring, let's say commutative ring maybe, but it's okay. And consider a ring homomorphism from the polynomial ring in two variables into A. It is very easy to notice that this ring homomorphism is completely determined by the image of phi on x and phi of y. So this should be actually y. So a group homomorphism from the polynomial ring to another ring is totally determined by the image of the variables. Why? Because if you know these elements, you can write the image of phi on every polynomial. Because if this is a ring homomorphism, then phi evaluated on this polynomial has to be given by this. And if I know phi of x and phi of y, I can calculate this inside A. So if we rewrite this, we say a ring homomorphism from V on two variables, the polynomial ring into A, is the same as maps from this set xy to A. So conversely, if I have a map like this from the two variables into A, I can construct a ring homomorphism from the polynomial ring into A using more or less the same formula. Here I have this map F from these two variables. So essentially it means two elements on A. I can reconstruct this map F tilde using this formula. Right? So the map of F tilde on a polynomial, I will just replace X by F of X. I will replace Y by F of Y. I can calculate this inside A, and I can recover F tilde. So the whole point of this discussion is that the polynomial ring satisfies this marvelous property, which is, so let's denote xy by x. If I have a map like this, and this is just a map because x is a set, it doesn't have any structure, it is just a map, set theoretic map, then a map from x to A is the same as a ring homomorphism from Z adjoin x, which is the polynomial ring, into A. So the polynomial ring, you can think of it, is a way to convert set theoretic map from the variables into a ring homomorphism. And this is done uniquely. So this extension, you think of this map here as an extension, is unique. And this is what we call universal property of polynomial ring. And when something is called a universal property, it means it's very important. Okay? As a general rule of thumb. Okay. So this is how you think about this polynomial ring and why it is nice. Because you can prove that any algebra or any ring that satisfies this universal property is unique. So if I have a different ring, let's call it R, which satisfies the same property, then R will be isomorphic to this polynomial ring. Not only this isomorphism is unique. So, it is a very rigid situation. Once something satisfies a universal property, you can prove it is unique up to unique isomorphism. So any other object which satisfies the same property is isomorphic to it in a unique way. So it is very rigid. If something satisfies a universal property, you cannot change it much unless you destroy this universal property, which tells you that the universal property determines the object fully, which tells you I can define what is a polynomial ring without writing you a polynomial. I can define you not a polynomial, but I can define you a polynomial ring as a ring which satisfies this property here. It will give you the polynomial ring alone, and I never told you what is a polynomial. Then I will tell you a polynomial is just an element of this ring. Of course, it is a very abstract way to present things, but it is very useful as well. And why I forgot about terms and all of this and started talking about polynomial rings because, well, do you remember something from the beginning? Here in the analogies, we were talking about free objects. And this is what I wrote here the polynomial ring. That's where it comes. So in generality, the terms will actually be the free object. And when we say this universal algebra of a polynomial ring, I actually, in more general case, I should write the universal algebra of a free object. Free object. So it just turns out that in the case of rings, this free object is the polynomial ring. So the theorem now, which is the main theorem maybe, is that this algebra, Tx, the term algebra, they call it the term algebra, that's also why T is there, is the free S algebra generated by X. And this means the same theorem we did for polynomial ring. So it means the following. We start with an A algebra A. We start with a set X, and we start with a map. And again, this is just a map from X to A. And we claim that we can construct F tilde, an extension from this term algebra into A, But this now is a homomorphism. It's not just a set, a map. It is actually a homomorphism, and we require this to, satisfy the same universal property that this triangle is commutative. So here again, I start with the set A, X. I have an algebra A, and I have EX. Of course, I always have a map from the variables into the term algebra, because remember, every variable was an element in the term algebra. And I can now fill this gap here by a map, alpha tilde. And the way you define this alpha tilde is also in an inductive way, because this term algebra was constructed inductively. It was defined inductively. So any map you would like to define on it will also be defined by induction. So if you start with a variable, alpha tilde is just the same as alpha. Okay? And you use this to do the induction. You should maybe reflect on it a bit. But if you see it in the case of rings, it will just be substitution. It will be like the same thing we said here, I guess. Yes, it will be this map here. So you just substitute the value of the variables. So you substitute it instead of x, the value of the map. So this will, in our case, will be alpha of x, alpha of y. So it will be more or less this map, just substitution. You have something like a polynomial, and you substitute the values of the variables. And this will allow you to make this extension. Okay? And this is the theorem. So the theorem tells you that the term algebra is satisfying this universal algebra. And therefore, it deserves to be called the free algebra. And let me reflect a little bit philosophically why it is called the free algebra. So let's say, to give you a bit of intuition, if you have something like let me maybe write this. If you have this ring here, and you would like to ask yourself, do I have any ring homomorphism into integers? The answer will be no. You don't have. Why? Because you have the element 1. Suppose you have, and we proceed by induction, by contradiction. Suppose you have a ring homomorphism like this. Let's talk about phi of 1. What is it? It should be a natural number, right? So let's calculate phi of 1 plus phi of 1. This is supposed to be a ring homomorphism, so this should be phi of 1 plus 1. But phi 1 plus 1 in Z mod 2 is 0. This is phi of 0. But phi is still a ring homomorphism, so this is 0. So we are looking for phi of 1 plus phi of 1 equal to 0, which is just phi of 1 is a natural number. Sorry, is an integer. So this is 2 phi of 1. So this means phi of 1 must be 0. But this is a contradiction, because for this to be a ring homomorphism, phi of 1 must be 1. This is the one condition of a ring homomorphism. Okay, why this happened? It happened because we have a relation here, which is the relation 1 plus 1 equals 0, and we don't have this relation. So once you have a relation, every homomorphism preserves the relation. So when you say something is free, it means it doesn't have any relation except those imposed by the axioms. So something is free, it means it doesn't satisfy any rule. It just satisfies the necessary rules imposed by the axioms of the theory, but it doesn't satisfy any extra axioms. For example, the axiom of a ring doesn't tell you that 1 plus 1 is 0. It might happen, it might not happen. So for something to be free, it means it shouldn't satisfy this restriction. It should not abide by it. It should be free from this relation. Actually, should be free from any relation which is not imposed by the axiom. And that's what the notion of a free algebra, of a free object means. So this is actually reflected by this universal property here, because it tells you no matter what values you take, I can always find a ring homomorphism with these values. I can always, if you give me the values of all the variables, I can always extend, unlike this case. So my initial elements here don't satisfy any relation, because once they satisfy a relation, I can find an algebra with elements which don't satisfy this relation, and then I will not be able to find such a map. So this property here precisely tells you intuitively that the objects of your three algebra don't have any extra relation which are not imposed by the axiom. That's why it's called free. Okay? So this is a bit of a philosophical tangent. In any case, now we are back to equations. So let's say we have two terms, t and t prime, and we will write this notation here. This is just now a notation, and the way to pronounce this, you say that A satisfies the equation t tilde t prime equal t. So you can also write this as equal if you want. I just prefer to write this to ensure that this is just, can you hear me? Hello?
Yes, yeah.
Okay,
Yeah.
okay. I thought something happened.
No.
So we just write A satisfies this equation, and you can write this as equality, but I prefer to write it like this to just remind me that this is actually not an actual equality of numbers. It is some kind of a definition. So in any case, this here means this is just a definition. That's why I write definition. If for every map x to alpha, alpha x to a, the extension tilde alpha tilde have the same image on t and t prime. So if we go to this diagram again, here we have t and t tilde. So and here we have any map alpha. I know that alpha tilde exists, and I would like that they have the same image under alpha tilde. If this happens for every alpha, then I call that A satisfy the equation t prime equal t. And if you think about it, just maybe as an example of the example, if you take here the polynomial ring, xy, here you have a polynomial A, and here we have x and a, xy. So this was our situation for rings, right? So here I can write something like x squared plus y squared plus 5. This is my t. My t prime will be, I don't know, y cubed. And maybe let's write this x squared plus 5. So we will write then that a satisfies y cubed equals x squared plus 5 if and only if for every alpha here, the image of t and t prime are the same in A. And if you write this in practice, what it means, like if you like unpack the definition, it will mean that for every A and B in A, B cubed equals A squared plus 5. This is what it will mean. So that's why it deserves the name equation, because if you write it in examples, it will actually give you a restriction on the algebra by an equality of equation, as in the example of commutative rings. Here, a term is just a polynomial, and when you say that an algebra satisfies an equation, it means that the elements of this algebra satisfy this polynomial equation, actually, right? So, for example, if you write something like x squared plus 1, and you take this to be 0, which is a term, so it is a term. So sorry, it is a constant, so it is a term. Then the equation will be x squared plus 1 equals 0. So it will mean that you would like to map the element x into a square root of -1. So something like I in complex numbers. So it gives you a restriction on what kind of equations the elements of A can satisfy. Okay. And now the definition is, if we have now a bunch of equations and we have an algebra A, we will write that A satisfies this bunch of equations, right, written like this. This notation comes actually from logic. So we will write that A satisfies this equation M if A satisfies every equation in M. So this is nothing crazy. And now, welcome to the marvelous theorem of Birkhoff. So this theorem tells you the following. Let's say, and now, if you weren't paying attention, please pay an attention. And maybe I ask you if there is questions before I talk about Birkhoff theorem. because it is actually our final thing to come. Any questions so far? Because I'm going to use everything I said today in the theorem. Okay. So the theorem is as follows. Suppose we have a collection of algebras. Again, we fix the signature and so on. We assert that this collection is equational. And let me tell you what this means. It means that we have a set of equations such that an algebra lies in this collection of algebras if and only if it satisfies this equation. It is like, you have groups. A group is a monoid or a set with a binary operation satisfying this axiom. That's the kind of a mental model you should keep in your mind. So this is like defining a group or defining a ring. You say, I have operations and they satisfy this list of axioms. So we usually introduce groups using axioms, but here we are doing the reverse. We are assuming that we have some algebras and we are looking for the equations they satisfy. And we say that we have a list of equations that they satisfy if and only if this collection of algebras satisfies three properties. First of all, it is closed under subalgebras. This means if I have an algebra in this collection, then any subalgebra is also in this collection. So this is something like saying a submonoid, the collection of groups is closed under subgroups. A subgroup is a group, and it is closed under products, which means if I have a collection of objects in C, then their product is also in C. I know I didn't tell you what is a product, but you can define it in the reasonable way. I will leave it to you as an exercise. It's a very good exercise, very easy exercise to know how to define this. You essentially do the following. You go to your definition of groups and just mimic it. Okay? And the third condition is that this collection of algebras is closed under homomorphic image. So it means if you have A is an algebra in this collection, and you have a surjective homomorphism, then also the codomain is in this collection. So again, the theorem tells you the following. I start with a collection of algebras, any collection of algebras. Let's say finite groups. That's my collection of algebras. So finite groups. Let's take the example of finite groups. It is equational means that I can find a list of axioms in form of equations. That's the whole point, which we defined equations. It have a very precise meaning, such that an element of a general algebra will be in this collection if and only if it satisfies the equations. So this, in our example of finite algebras, would mean that we found, actually we don't, but if we were to find a collection of axioms, a collection of equations, such that a group is a finite group if and only if this group satisfies this extra equation. Okay? This happens only if and only if this collection of algebras is closed under three operations: taking the subalgebras, taking the product, and taking the homomorphic image. Now, why this theorem is marvelous? Because finding equations is hard. I give you a bunch of examples of algebra and I ask you whether there exists a list of axioms in the form of equations for it. This is not an easy task. You see, for groups, we had to eliminate the existential quantifier. You remember? It was some trick. It used the uniqueness of the identity and the uniqueness of the inverse to eliminate the existential quantifier and to make into the axioms into equations. So we needed a proof. We needed the proof that inverses and identities were unique. So it is a real mathematical proof that you need for this. But these conditions are usually very easy to check. Okay, so maybe let me give you a corollary of this. So the class of fields is not equational. Why? Because a product of two fields is not a field. By this theorem, if this class of fields were equational, we will have that the product of two fields is a field. But we know the product of two fields is not a field, which means that we cannot find a list of equations to axiomatize a field. That's why you remember when I talked about fields early on. Here, I said we cannot eliminate the existential quantifier. We cannot eliminate this. We cannot make it into an axiom like this. And this explains you now why actually the product of two fields is not a field, precisely because the axioms of a field is not equational and cannot be made into equation. Of course, you can define something in a non-equational way, like groups. The usual way we define groups is non-equational, but we can always make it into equational theory. But for fields, we cannot do this, and that's why fields are ill-behaved, right? Okay, so maybe I will, as a final application, which I made up to show you what is, how flexible this is. So the only one who somehow interacted with me today was Ridwanullah. So I will define a Ridwanullah algebra to be the following structure. I actually made this definition yesterday, so it is not important definition or anything, just to show you how flexible this algebraic structure is. Okay, so what is a Ridwanullah algebra? It's a set T. So first of all, let's fix the number of N is the number of participants of today's seminar. I think it was maximum 15 people, so N equals 15. Okay, so this is 50. So you see, even yesterday, I didn't know what is this algebra going to be. So a Ridwanullah algebra is a set T equipped with 15 operations. And let's denote them M1, M2, until M15. And M1 will be of arity 1, M2 will be of arity 2, M15 will be of arity 15. And we require this equation to have for every I. So these are actually 15 axioms. And as you see, this is an equation. So this is here we have for every, and here we have equality, here we have a term, here we have a term. So these are equational things. And this axiom just tells you that if we have mi of x1 up to xi is the same as mi minus 1. So here I need to give you ni minus 1 many elements. So here we have m1 x1, m2 x1 x2, and so on until mi minus 2 x1 up to xi minus 2. So these are I minus 2 many elements, and here I have one extra element. And here, if you notice, I reverse it the order of the variables. So I actually have the correct number of inputs. So it is some weird, complicated equation that I just made yesterday at 4 a.m. for no reason. And let's call this Ridwanullah algebra in honor of Ridwanullah. Now, imagine you were given the task of going and proving the first isomorphism theorem of this algebra, and to ask whether free objects, free Ridwanullah algebra, Ridwanullah is a free guy. We would like to know if free Ridwanullah algebras exist or not. And we would like to know if a sub-algebra of Ridwanullah algebra is a Ridwanullah algebra, and same for product. If you do this, I promise you it will take you 2 days writing a lot of proofs, and you will, at the end of 2 days, feel, oh, I accomplished a very interesting mathematics. But you didn't, because you can deduce all of these facts very easily from universal algebra without knowing anything about Ridwanullah. First of all, first isomorphism theorem always hold. And remember, did you notice something? There are no constants in Ridwanullah algebra. So you cannot define something like a normal subgroup. You have to use congruence relations. And we know that Ridwanullah algebra exists because this is actually an equational thing. And the product of two Ridwanullah is Ridwanullah algebras and so on. So without knowing anything about this algebra, which is totally made up, you can prove theorems. And that's how useful and crazy and powerful universal algebra is. So as an exercise, go home, make up your favorite crazy algebra with 27 operations. Some of them are 17 array, some of them is 26 array. And hey, you have proved some theorems from nowhere. Okay? So this is everything I wanted to tell you today. I will just end by telling you next what I could have told you if I have other 3 days. Just the headlines, you know? So first of all, a very important part of universal algebra is lattice theory. So a lot of today we just scratched the beginning of the theory, and usually we would like to analyze the structure of algebras. And usually in universal algebra, this is done via so-called lattice theory. So I told you about congruence relations. So if you have an algebra A, you can consider the set of all congruence relations of A, and this will form something called a lattice. And a lot of the properties of A can be encoded or read from these properties of this lattice. So people usually care a lot about the lattice of congruence relations on algebra and study the algebra via this lattice. So this is a very important story. We can think about analytic synthetic methods. By this I mean you start with an algebra, you want to study an algebra, you don't know what to do, so you try to decompose it into pieces. So these are the pieces. And you study each piece, get some information, and you try to assemble this information into an information about A. So this decomposition is what I call synthetic and or analytic. And then so it's essentially dismantles the algebra, study each part, and recombines the information. So this is also sometimes done using some lattice theory. Sometimes you have, for example, you would like to have methods to construct more complicated algebras. There are constructions such as the ultra product. So I told you about the product. This is the easy thing, but there is something called an ultra product construction, which is also very important in this regard. You can also ask yourself, okay, we studied equational classes of theories. These are usually called varieties. And by the way, if there is anyone here interested in algebraic geometry, this notion of a variety has nothing to do with algebraic geometry. The notion of a variety in algebraic geometry is something different, just a coincidence. So equational class is sometimes called a variety, and actually that's why I called in the beginning Birkhoff variety theorem. Okay, so now you go to non-equational theories and you would like to develop some theory for this, and some of this exists. For example, you have a notion of a quasi-variety, right? And people have studied this as well. And if you are bored with universal algebra, you can think about limitations of universal algebra, because as I told you, not everything is covered by universal algebra. For example, someone talked about quantum groups, if I remember correctly, and there was another interesting example. Quantum groups cannot be studied by universal algebra, and I will tell you why in a moment. And you can also ask for extensions of universal algebra. So more general framework than universal algebra. And this exists. And just to drop some names into you, the next steps would be something like category theory. Okay. And if you study category theory, you can do something called operator theory. And operator theory is very, very general. In category theory, you also have something have monads. And all of these allows you to study more general algebraic frameworks. For example, for algebraic frameworks, operator theory is insanely powerful, insanely powerful. So these are some directions you can go with. And I will finish by telling you where to learn more about universal algebra. So here I listed 4 books. As is written, I personally learned a lot of this material from this book many, many years ago. I think it's a very nice book. This book here is a course Universal Algebra. It's very, very standard. It's actually from the 60s. And you have 2 more gems. So these 2 books here. So this is Universal Algebraic Logic by Andreka Nemetti and Genies. And here you have an invitation to general algebra and universal constructions by George Bergman. And notice this is Clifford Bergman. This is George Bergman. I don't know if they are brothers, maybe 2 brothers specializing in universal algebra. That would be a cool story, but I don't know really, just maybe a coincidence. And I promise this is not sponsored, okay? These are just my selection. And let me give you maybe a final comment about this book. So this book here is very good, very nice, but it doesn't contain any category theory. And as I told you, category theory is in some sense the corrective framework to do all of these things I told you about. So today, for example, I told to you about the free constructions or the free object. and this can be viewed from the language of category theory as some kind of an adjunction. Okay, so this book takes you into the realm of category theory. It will teach you category theory and universal algebra. So it is a very, very good book. This book here is amazing, but the main aim is not universal algebra. The main aim is, well, universal algebraic logic. And as I told you, universal algebra, I learned about it from people doing algebraic logic. So just use this universal, it gives you enough universal algebra to do algebraic logic, but you can neglect the algebraic logic part and only read the universal algebra. What is amazing about this book is, first of all, the universal algebra part is very short. It is 70 pages. It is very, very precise. So if you were today unhappy about this distinction between a symbol, interpretation, blah, 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 it is insanely precise. And then this is very important. It gives you a lot of motivation, a lot of philosophical comments that you will not find in any other book. So it somehow try to transfer the internal model of the authors. And these authors are like very, very important guys. So they understand the material very deeply. So they try to transfer this intuition in the book. It's very important. So I really maybe advise you to look into these three books and make your choice if you would like to actually, read about this. One final comment is about the quantum groups, because I promised it. So why universal algebra cannot do this? For a very simple reason. So a quantum group, I will of course not define this, but in a quantum group, you have something called a co-multiplication. So you will have something, you have something like this. And if you see, this is actually somehow in the wrong direction. In universal algebra, you would like something like this, or a product, or a tensor product, or whatever. So in a quantum group, you have the other way around. You would decompose. Here you have this, something like this. You decompose, right? But in universal algebra, we compose, we multiply. Here we co-multiply. So the idea here is that quantum groups are related to something called Hopf algebras, more or less. I know it is more complicated than this. And these Hopf algebras are co-algebras, so in the sense that we have something like this. And this is not studied using universal algebra. But if you go to obrads, there is obrads also cannot handle co-algebras, but there is something called co-obrads, which you can use a bit. But I am not sure how successful this approach is. So quantum groups are actually very unique in this. It is, I think, it is a very deep topic, and it's not your easy algebraic structure that you would prove everything about it from first principles. That's why it is hard. That's why it was only discovered in the 8th, where groups have been discovered for 2 centuries. So yeah, but I hope this somehow gives you also an idea about the limitations of universal algebra. So, maybe the take-home message from today is universal algebra is very strong, very powerful, quite universal, but not really. Okay, thank you for your attention, and I will leave it here. Thank you.
Thank you very much.